Hello everyone, welcome to Mind is Fun Education. Last video we have seen the independence of random variable. Let's take an example. So we have given this joint PMF table, right? So maybe it has came from some experiment, and we have two random variable associated with this experiment, random variable x and y. And these tables that we have already seen represents the happening of two event in this case at a time. So if I have to pick one example, so random variable will take the value 1 at the same time, random variable y will take the value 1. What's the probability of this event? So you can find this info in this joint PMF. So that is 0, right? So you will have the probabilities of all the possible pair that random variable x and y can take simultaneously. This is what we have seen in the joint PMF. Joint PMF table or function will have all the infos that you need to have. Like we have already seen that how to extract the marginal PMF, in this case the marginal probability mass function of y or marginal PMF of random variable x, right? We have also seen the case or the definition of independence of random variable. So this is what we are talking about through an example. We have this joint PMF and we just want to know that are these two random variable, that is x and y, are these independent? So to answer this question that these two random variables are independent, we can use the definition of independence of random variable. That is, we just want to check that the joint probability of this random variable x and y is equal to the individual product of the individual marginal PMF of this random variable x and y respectively, right? And this condition needs to be checked for all possible x and y pair. You can easily do that, right? Because this probabilities are already given for all possible value of x and y. So this joint probability is already given. What you will have to do, you will have to find this probability or this probability or this marginal PMF and this marginal PMF. How you can find? So depending on whatever the value x will take, we will have the different marginal PMFs, right? So probability that random variable, we are talking about this random variable x, it takes the value 1, so that will be equal to 1 divided by 20 plus 2 divided by 20. So we are talking about this column, right? And you will have to find this marginal PMF for all the cases. So and similarly for random variable y, right? And corresponding to whatever the pair you are talking about, right, you will have to take the product of these marginal PMF. And if this condition gets satisfied for all the possible pair of x and y, then we can say that this random variable, these two random variables are independent. You will have to check for all possible pair of x and y, and this condition should be satisfied for all. If one of the condition is not getting satisfied, then we break from that point and we say that these two random variables are not independent. This is the one way. Other way, you can use the intuitive definition. So what you will do, you will simply, let's say we are finding the probability of this random variable x when it takes the value 1. So we are looking at the complete universe, and we are trying to find the probability or the marginal PMF from this table of this random variable x. We have not given any kind of condition, something like that, right? So that will be equal to, so basically we are talking about this column, right, where random variable x takes the value 1. So that will be equal to 1 divided by 20 plus 2 divided by 20. So that will be 3 divided by 20. Now let's say we have given this condition that random variable y takes the value 1, and now we want to find, or we want to check our belief if it is getting changed or not, that random variable takes the value 1. So we want to find this probability. So what we have done, first we have the initial belief about this random variable x taking the value 1 is this one, or the initial probability was this one, when random variable x takes the value 1. Now we want to check under this given condition what happens to our belief, or what happens to the same probability that random variable x takes the value 1, right? And if you have to write this same thing in terms of the PMF notation, this is how you can write. One given, right? So you can look at, so we have given this condition, right, y is equals to 1. So y is equals to 1. So now this was our initial universe. Now we have given this condition or this evidence. Now this is our universe. Under this universe we want to find that what's the probability that random variable x will take the value 1, and you will see under this universe that y is equals to 1. If you check for x is equals to 1, the probability is 0. Or you can, same thing you can look using the formula of the conditional probability, that x takes the value 1 intersection y takes the value 1 divided by the conditioning probability that random variable y takes the value 1, right? So this probability is 0, so overall this probability will be 0. You got the point, right? So what happened? Initially, when there was no condition, your belief about random variable x taking the value 1 was 3 divided by 20, and when you have given this evidence that y is taking the value 1 under this given condition or evidence, what's your belief about that random variable x takes the value 1, and now it is 0. So this evidence is affecting your belief about this event, right? So we can directly say that random variable x and y is not independent. So I want to talk one more point here. When we were discussing about the conditional, when we are discussing about the independence in terms of the event, in, I don't know, in one of the few videos when we are talking about the basic probabilities, at that time we also talked about the conditional independence, right? So we have also introduced the notion of conditional independence, and we said that conditional independence is the same as the ordinary independence, except that it would be applied to a conditional universe. And something similar we can talk in case of the random variable as well. So let me first of all recall you what I am talking about. So we have seen, if I have to talk about in terms of the event, we have seen that the probability of this event A, let's say these two events are independent, then probability of this event A intersection B, or the joint probability, will be same as the product of their individual probabilities, right? We have not given any condition and not any evidence. So this is what we have seen as a independent of two event, and similar things we have applied for the in case of a random variable with event and with two random variable and with multiple random variable. So when we applied for the random variable, we talked about these event in terms of the random variable, right? Now we have already seen this case. Let's say under this evidence C, let's say if these two events A and B are independent, right, then what will be the definition of this independence or the conditional independence? So in that case, again we will have to check the probability of this event A under the condition C, probability of event B under the condition C, and if these product of these two conditional probabilities are equal to this probability, then we can say that these event A and B under this condition given event C will be independent. We have already talked about this in very detailed manner. So right now we are talking about in terms of the event. Similar thing can be applied or done when we talk in terms of the random variable. So we can directly just look at this example. Let me bring this example, and we will see that what's the conditional independence, and also we will make a very important point that let's say here what we have seen here, we have seen that these two random variables are not independent. So we will make an important point that does conditioning affect the independence? We have already seen when we were talking about in terms of the event that yes, conditioning may affect the independence. Here x and y random variables are not independent. Let's say we have given any condition, and under that condition if we want to check that these two random variables are independent or not, you will see that conditioning may affect the independence, right? It is not necessarily true that if these two events or if these two random variables are independent, then under a given condition again these two random variables will be independent. Let's say we have given this condition that we have this condition that random variable x is taking the value that is less than equal to 2 and random variable y is taking the value that is greater than equals to 3. So what we are talking about, random variable x is less than 2, so less than 2 from here, and random variable y is greater than 3, so greater than 3 from here. So basically we are talking about this section. So we have given this condition, right, and under this condition we want to check, or the question is random variable x and y independent? Let's call this condition or this event where random variable takes the value less than 2 and random variable y takes the value greater than 3. Let's call this event as event C. What we want to check is that independence of the random variable x and y under the condition C. We can make use of the definition of independence. Under the condition C, let's say random variable x will take the value little x and y will take the value little y. What's the probability of that. And if this probability is equal to the probability or the marginal PMF of this random variable x under the condition C, because we are talking about the conditional independence. So we are just extending this idea from event to the in terms of the random variables times the marginal PMF of this random variable y under the condition C, right? And again, it has to be true for all the possible pair of x and y. Alright, first of all, look at this condition. First of all, this was your initial universe, right? Now, under this condition, where it is less than x is taking the value less than 2 and y is taking the value greater than 3, this will be your possible pairs, right? Or this will be your universe, right? So first of all, you will have to find this joint probability under this condition for all possible value of x and y. Here, if you talk under this condition, what will be the all possible value of x and y? It will be 1 comma 3, x is 1 and y is 3, or maybe it will be 2 comma 3, or maybe it will be 1 comma 4 and 2 comma 4. So these are the possible values under this condition C. Random variable will take these values, and we will be talking about the probabilities of these event again under this condition C, because under this condition this is our universe and these are the possible pair that random variable x and y can take, right? So first of all, we need to find the revised probability or the revised joint PMF under this condition C. So under this condition C, we will have the 4 possibilities, right? And for what happens to the other possibilities? Since those other possibilities are not falling into this condition C, so all will be assigned to these 0 probability, and these probability will have some revision. What kind of revision? You can make use of the conditional probability definition, and you can directly assign these probability. So here random variable y is taking the value 3, 4, random variable x is taking the value 1, 2. So you can directly do that even. How? So here the proportion for these probabilities will be same as the original probabilities, as the original universe, but now here the ratio we were seeing the total from 20, but now since this has to be also a legitimate probability, so the sum would be 1, so we will have to divide with this 9, the sum of all these, right? So that this conditional probability is a legitimate probability. When you will add all this probability, it should be add up to 1, right? And if you are not comfortable with this reasoning, although I have described in my very first lecture of the conditional probabilities, if you are still not comfortable with this reasoning, how you can see? So first of all, here random variable x can take the value 1 and 3, right? Under this condition C, so if you make use of the conditioning definition, so probability that random variable x takes the value 1 intersection random variable y takes the value 3, intersection the given condition, that is C, divided by the conditioning event, that is probability of this event C. So this event, random variable x is equals to 1, y is equals to 3, and this condition. So overall you will be this probability is this 2 divided by 20, and this probability will be sum of 1 divided by 20 plus 2 divided by 20 plus 4 divided by 20 plus 2 divided by 20. So that sum would be 9 divided by 20. So you will get 2 divided by 9. So that is what I have written here. Similarly, you can check for the joint probability under this condition C, where random variable x takes the value 2 and y takes the value 3. You will find it will be the 4 divided by 9. How I have written this probability directly? So I have, first of all, this conditional probability is also a legitimate probability, so their sum has to be 1. Second point is that the part that it was taking on the original universe, the same part it will be taking in the conditional universe. But by keeping this mind that this has to be the legitimate probability or the PMF, I mean to say the sum has to be 1. So you will have to scale accordingly. Alright, since you have got all the possible joint probabilities or all the possible probabilities of all possible pair under this condition C, let's find out this marginal PMF under this condition C. So what will be the marginal PMF of this random variable x given this condition C? So when random variable takes the value 1, so marginal PMF will be 1 divided by 9 plus 2 divided by 9, that will be 3 divided by 9 or 1 divided by 3. Similarly, we will have the marginal PMF here when random variable x takes the value 2. In that case, we will have 6 divided by 9, that is 2 divided by 3. Now, what will be the marginal PMF of y when random variable takes the value 3 under this condition C? That will be 2 divided by 9 plus 4 divided by 9, 6 divided by 9, that is 2 divided by 3. Marginal PMF when random variable y takes the value 4 under this condition C, 3 divided by 9, that is 1 divided by 3. We have to check for the independence. That means this probability should be equal to the product of their individual PMF. You can easily check from here. So this probability where random variable x takes the value 1 and y takes the value 3 under this condition C, this probability is 2 divided by 9. The marginal probability when x takes the value 1 under this condition C is 1 divided by 3 times y takes the value here 3 under this condition C. This marginal PMF is this one, 2 divided by 3. So 1 divided by 3 times 2 divided by 3 is 2 divided by 9. So 2 divided by 9, this is the probability that we have got. You can check for this case also directly. So the marginal PMF is 2 divided by 3 times 2 divided by 3, that is 4 divided by 9. Check for this one. Marginal PMF of y is 1 divided by 3. Marginal PMF of x is 1 divided by 3. So 1 divided by 3 times 1 divided by 3, that will be 1 by 9. You can check for this one. So overall point is that here this random variable x and y are conditionally independent. You see the difference, the point that I was making. It is not necessary that in the original universe, if these two random variables are independent, it doesn't mean that under this any condition these two random variables will be independent again. So here we have seen that it was not independent, and under this given condition these probabilities are these random variables are independent. And also we have revised our concept about this conditional independence. If you are not comfortable with this conditional independence, I would recommend to watch my this lecture where I have talked about this conditional independence in terms of the event. Same idea we have extended for the random variable here, right? That is all in this lecture. If you have any doubt, let me know in the comment section or let me know in the group. I will try to resolve that. Thank you.